Does the phrase stoichiometric equation sound familiar to you? That's that part where we are burning a fuel and we use just the right amount of air needed to complete the combustion, no more and no less. That's what this module is all about. So it is my hope that you remember the words stoichiometric equation either from high school chemistry or freshman chemistry. So that's my best guess of where you probably have some background already in burning hydrocarbon fuels. And so let's look at the most simple example, probably one that you were exposed to in college chemistry. And the idea is balancing the moles of the reactants, in other words, the fuel and the oxidant that you're combining so that you get perfect combustion, nothing left over, but the exhaust products are some number of moles of CO2 and some number of moles of H2O. And you, of course, you remember the exhaust products are always going to include carbon dioxide and H2O, water vapor. Okay. And then I don't know if you had any formulas or if you sort of figured this out in your head, but your job was to balance the moles of the various elements on the reactant side with exactly using algebra, hopefully in your head, with the number of moles of the elements over on the exhaust side. And so I'm going to try to give you sort of a neat, what I think is a neat way to always get this right for any hydrocarbon fuel. Oh, so here's my disclaimer about Chapter 13. When we're combining hydrocarbon fuels with either oxygen or air, we're going to say in Chapter 13 that we've got complete combustion. In other words, we've got CO2 and H2O as an exhaust product, and some things that are not going to be in the exhaust is going to be unburned fuel. In other words, CH4 doesn't come over to the right-hand side that's unburned. And I know that a number of you certainly know in your experience so far that in most cases, carbon monoxide, CO, is also a product of combustion. You certainly know this about internal combustion engines, correct? You know about the dangers of car exhaust, diesel exhaust, because it contains CO, which is lethal in confined spaces. So that's my disclaimers. We're going to be looking at complete combustion only. Talk a little bit about the way we're going to model fuels in our introductory section on combustion. So this is a little bit of a high-level look at section 13.1.1. You've got liquid fuels. You've got familiarity with that. Some gaseous fuels, some familiarity with that, I'll bet. And also solid fuels. Like, well, there's a picture of coal, and you know that there are others like wood. And so I want to suggest that all three of these categories of fuels can be modeled chemically as C sub M, H sub N. Now, for the liquid and gaseous fuels, M and N are probably going to be integers. They could be large integers, but they're going to be integers. For solid fuels, not so much. But do recognize that, in other words, M and N could be some type of real number. It could be an integer and a fraction of 1.07 or something like that. N could be 2.25 for various solid fuels. But for right now, recognize that we're going to say that we can model any hydrocarbon fuel with the formula, the chemical formula, C sub M, H sub N. Examples of liquid fuels. Gasoline is modeled as C8 H18. That's octane. You don't need to memorize that, of course. But you've bought many a gallon, I'll bet, of gasoline fuel. Diesel fuel, that's modeled as C12. H23. And we're not going to get into the pictures of the chemical chains and things like that. We'll leave that for the chemical engineers to worry about. We're just, as mechanical engineers, we're just going to recognize that we can model these liquid fuels as C sub M, H sub N. Gaseous fuels. Same idea. Now, in the top left here, there's all these pretty molecular pictures of methane, butane, ethane, and propane. Now, let's think about things you're probably most familiar with, I'll bet. I'll bet you're most familiar with propane tanks that are used for gas grills. Propane is going to be C3H8. Pretty simple. M is 3 and N is 8. Okay. Typically, we model natural gas that comes up out of the ground as mostly CH4, methane. That's the way we mechanical engineers will model a natural gas that you see burning on your stovetop if you have a gas stove. And finally, solid fuels. Well, what kind of solid fuels are you familiar with? Certainly charcoal, coal, wood chips, wood pellets, and sawdust. All of these would be examples of solid fuels that are commonly used in combustion. Recognize that we can model those as C sub M, H sub N. Now, on the wood chip side, I've got a lot of practical experience with wood chips. Do recognize that a tree that's just cut down and turned into wood chips, it does turn out that a wood chip can contain up to 50% H2O water. So when you kind of get into this, the wood and wood pellets, recognize there is a measure of moisture associated with that. And there's some moisture associated with coal even. Charcoal, of course, is a manufactured product from wood primarily, and because of its manufacture, is going to have a very low level of moisture in it. But the idea here is to recognize that even with solid fuels, we can model our chemical equation for the fuel C sub M, H sub N. Now to our stoichiometric equation. Let's go back to burning any fuel C sub M, H sub N with oxygen only. We're going to get to air in just a second, but how could we create some type of formula or recipe for quickly determining what's the value for A, what's the value for B, and what's the value for C if I've got C sub M, H sub N as my fuel, and my oxidant is only oxygen? Well, you can study this reaction equation, and in order to balance the carbons, C, you can see that B is going to have to equal M. So you could write that down. Okay. I've set up an Excel spreadsheet to make this happen because in solving combustion equations, I'm always modeling my fuel as C sub M, H sub N. How about C? What's the value of C going to be? Well, by looking at the hydrogens in our equation, you can see that C is going to have to equal N over 2. I just write that down in my Excel sheet. And then finally, we just use algebra to solve for A, and A is going to be equal to M plus N over 4. I just used algebra once I had my B and C determined to solve for A. And so, look, you ought to be able to figure this out on your own, but if you jot this down, you're going to really save yourself a lot of time in your homework problems for this chapter. Now, you say, wait a minute, oh, this is handy, this is nice, but look, in the real world, we're usually burning a hydrocarbon fuel with air, not just oxygen. So that's another little level of complexity I want to add here. So if we go into your chapter 13.1.2, how do we model air? How do we model air that we're going to use as our oxidant in our combustion? Well, I hope in chapter 12 you recognize that air is made up nearly totally of nitrogen and oxygen, and it's mostly nitrogen. It's about 79% oxygen and 21% oxygen by mole fraction. In other words, by volume, 79% nitrogen, 21% oxygen. That's the air we breathe. And so you can do the math, you can do the algebra to see that the number of moles of nitrogen for each 1 mole of oxygen can be calculated by the mole fraction, okay? And so you can see that there are 3.76 moles of nitrogen for each mole of oxygen. So as you're going through your text, you're going to start seeing this number 3.76. It's not experimental. It's the science of what air is made up of. That's what 3.76 is. Number of moles of nitrogen in air divided by number of moles of oxygen in air. And this is what makes it only incrementally more complex to deal with burning a fuel with air instead of just oxygen. So let's go back and look at our stoichiometric equation. In other words, where we have perfect combustion, we're using air as our oxidant, okay? Let's say perfect combustion. We're turning our fuel into CO2 and H2O, and then recognize with air, the nitrogen's just along for the ride, okay? And so I've still got my A, B, and C from before. I just recognize it so you can just sort of look with your eyes what's changed with our stoichiometric equation burning air. All I've done is I put a parentheses around the O2 moles with 3.76 nitrogens for each mole of oxygen. So I'm taking A and I'm going to multiply the number of O2 moles by A and the number of nitrogen moles by 3.76 and A. So there we go. And again, this can be golden. I've put this into my Excel, handy dandy generic Excel calculator sheet so that I can stay straight without having to figure this out, scratch my head every single time I've got a new fuel to analyze. Okay, and the important part to recognize here on this slide is that recognize that nitrogen in the air doesn't contribute to the energy provided in our combustion. It's along for the ride. Nitrogen is just along for the ride. It's a pass-through. It passes from the reactant side over to the product side. So the next level of complexity, which I'm going to put in the next module, is adding excess air. So right now you have the ability to balance stoichiometric combustion equations with air from your previous experience, okay? Just a matter of balancing that chemical reaction equation. Now, in the next video, and in most of your homework problems, you're going to be saying, wait a minute, we want to put in a little extra air in our combustion process. This is a classic boiler. This is a steam boiler, a steam generator using natural gas, CH4 as the fuel, with air. And why in the real world do we use little excess air? Two reasons. One is to complete the combustion process. We don't want to have any situations where we're just putting fuel up into the exhaust gas. That could be a level of danger. And also it's a waste of money. We're buying all the fuel. We'd better burn all of it to get as much energy out, heat release, as possible. And so it's a matter of economics to get combustion as well as safety. So we want to get complete combustion so we're not sending combustible gases out up into the flue and you don't want any combustion to take place in your exhaust stack, do you? In your chimney. You don't want that at all. We always run with a little excess air. Okay, I hope that hope that reminds you what you've already learned, and hope that gets you ready for solving more complex but introductory combustion problems with hydrocarbon fuels.